So it's just a minute or two afterwards, but normally I will start sharply at 11 o'clock so we can get the most of our time together, and also so as not to penalize those of you who are actually here on time. Okay. This is neural networks. A better name for it might be deep learning, but neural networks has been in the course catalog for like 9 years or something, and things have changed. So a little bit about myself. So I applied here actually as an undergrad, and although I got in, I didn't end up attending. So I went to UCSD for undergrad and grad school. I left the PhD program before I finished my dissertation to start a Macintosh software company, and never gone back. So anyway, I'm not Dr. Rhodes. So you could just call me Neil. There's still one more place up here. And then if anyone else comes, you can grab that chair. How does that sound? Okay. So Emmanuel is hoping to get in with someone dropping. And so I taught for a lot of years for Apple at their developer university, teaching sort of week-long classes on different kinds of programming, like way back when, if you've heard of the Newton, or Palm Pilots, or doing Mac software, stuff like that. Yes for Palm Pilots or yes for Newton? Okay. So, and then I also taught at UCSD for several years as an adjunct. I taught here about 4 years ago. So in fact, I remember trying to get all the AV working because Shanahan was brand new. So I was, using a brand new classroom. So it looks like it's working better now. And then I was at Google for 8 years, working in their Orange County office. Left as a staff software engineer. And it's been about 3 years, I guess, since I was working there. And now basically I just focus on, now we have more than 24 people. Or even 25. What's that? You're also, okay. So yeah, those of you who are actually enrolled, have a seat. So is there anyone else who is not enrolled? You're not enrolled. Okay. Yeah. You can stand too if you want. Yeah, that'll be fine for today. And the three of us will talk afterwards. All right. Is anyone planning on dropping, by the way? Okay. The fact that you're here kind of shows some commitment. So anyway, yeah, interest in deep learning neural networks. A project I am interested on, though I haven't gotten very far, is on teaching a computer to play bridge, so the card game, both the play and bidding and so on. That's something I've actually been interested in since grad school. I did a little work in Lisp to try and get that going, but I think deep learning has a lot of potential for getting that working. Oh my goodness. Wait, you're back. No, you're not back. You're new. Okay. Are you enrolled?
Yes.
All right. So let's go through and actually take roll. Because we should only have 25 people here. Well, wait a second. You're okay. So why don't you stand up for him? You can come have a seat. All right. As long as we have 24 bodies and 24. So this kind of reminds me of the story. Back in the old days, right before they knew how to count, shepherds would want to keep track of how many sheep they had, right? And make sure that they all got them back safely into the pasture or wherever they take them back to. And so, does anyone know how they did it? Given that they can't count. So what they had was a bag of pebbles, or maybe they had pockets in, I'm not sure, but pebbles. And basically, as each, what did we say these were, sheep? As each sheep would pass them, they would move a pebble from their right pocket to the left pocket. So they didn't know how to count, but they knew right and left. And then, when all the sheep are gone, they look and see, do we have any pebbles left? Right? And if you don't have any pebbles, then that's good. If you ran out of pebbles, that's even better, because now you have more sheep than you started with. And of course, that's how you show two sets have the same cardinality, right? Show that there's a mapping, a one-to-one and onto mapping between those two. Anyway, rocks are sometimes called, or pebbles sometimes called calc or calculi. And so calculating is this matching stones to sheep. And anyway, that's what I wanted to do here. Basically make sure we had a one-to-one correspondence between someone in the class list and sitting in a desk. And then we got 3 extra sheep in the back. All right, so let me go through and just get a quick background from you guys as to like why you're here, what your background is, if any, with machine learning or your knowledge of neural networks. So a 15-second thing. So let's start with you, and your name is?
I'm Winston.
Winston.
I'm a junior at Pitzer, CS major here. And I'm taking this class because I don't have any background in machine learning or AI, but I think it's an area I might be interested in, so I wanted to try it out.
It's good enough.
I'm Richie. I'm an econ CS major from CMC. And similar idea.
Richie and Winston? Okay.
I've done much machine learning or anything, but as a CS major, I'm really interested in exploring AI and deep learning. So.
Okay.
I'm Abel. I'm a math CS major.
Abel, A-B-E-L?
Yeah.
Okay.
I'm a math CS major from CMC. I have some very basic background in machine learning, but nothing too fancy. But I'm really interested in machine learning. That's why I'm here.
Joseph. Am I right?
Yes.
Okay.
I'm a math CS major at MUD. I read a book and made a neural network based on that book, and that was a lot of fun, so I think this class will be fun.
Okay, Laura.
Yeah, I'm a math CS major at MUD, and yeah, I've just been told that some machine learning, AI, when I talk to people about what I like about CS, they told me they thought this would be something I'd be interested in.
Okay, and I'm just going back. Winston and Abel and Richie. All right. Ivy?
Yeah. I'm a math comp bio major.
Math, computational biology?
Yeah.
Okay.
And computational biology.
Okay.
I just thought deep learning is something that might be applied to computational biology or bioinformatics.
Okay. Nita?
Yeah. I'm Nita. I'm a math CS major at Harvey MUD. And I'm taking this class. I did some vision work over the summer and used some deep learning and kind of just to explore that more.
Okay. And just to get a background here, who here is not a junior? You're a? Okay. Sophomore? Senior? Okay, fine. Nita, let's go. I don't know your name.
I'm Jason, and I'm a junior at HMC, and I'm a B2 major, and I don't have much background in machine learning at all.
Okay.
But I thought it was one of the more interesting courses.
All right.
I'm Azal. I'm a junior at CMC.
Azal, A-Z-A-L?
HAZAL.
A?
HAZAL.
H-A-Z-A-L, Hazal. Okay, thank you.
I'm double majoring in computer science and neuroscience, so this course just seems to be different.
Okay. Are you another J? No. Yes. Joseph?
Yes.
Jake? Jonathan?
Correct.
Got it in 3.
Jonathan.
Okay.
I've been doing neural net related things for about a year and a half. First on my own, then an internship. And I'd like to formalize my intuition.
Okay.
I'm Nithya. I'm going to
Well, hold it. Spell that for me.
Nithya.
Nithya.
Nithya, yeah.
Okay.
I'm a junior at Scripps. I'm a CS major through MUD. And I've had a previous internship where I've used machine learning, deep learning algorithms, but I haven't actually created any, so I wanted to learn more about them.
Okay. And go ahead.
Evan.
That's right. Yeah, you are Evan. Yeah. Go ahead.
Hasn't changed yet. Junior at Harvey College, studying computer science and math. I've learned a little bit about neural networks, just enough to think they're really cool and want to learn more.
Okay, Princewell.
Junior at Harvey MUD, computer science and math major. I also have some basic understanding of neural nets and would like to formalize my intuition.
Okay. Did I ever know your name? Okay.
I'm Carrie, and I'm a junior from Harvey MUD, CS math major, and I have some background about
Yeah, it's hard taking the online courses to actually get yourself to go through all that stuff. Yeah.
I'm Yuan. I'm at Med for only one semester, and I have already completed some online courses about diploma.
Okay, and where are you from?
France,
Where?
Paris.
I've heard of that. Okay. Jake.
I'm junior at Med CS Math. I did a little bit of tree-based machine learning at the end of last year in the course.
Like random forests or something? Okay.
That's the extent of that.
Got it. And in what class?
Scientific computing.
Got it. Okay.
I'm Julianne.
Oh, wait. I was supposed to know your name. You're like the first person whose name. Okay. Julianne. Julianne. Go ahead.
I'm a junior at Rhodes CS.
You don't have to say junior because we know everyone's a junior except you're a senior and you're a sophomore and someone else is a senior. Okay.
CS math major, and it could be useful in research this semester.
Okay. Brendan.
Yeah. I'm Brendan. I'm a Chem CS major. I haven't had much exposure to all that, so.
Okay.
I'm Monica. I'm a CS major, and I don't have much experience in renewable energy.
Okay. Dhruv?
Yes.
D-H-R-U-V?
Yes.
Okay.
That's fine, I read.
Yeah, the normal spelling. Go ahead.
So I'm Dhruv.
And I appreciate that.
I'm a senior, double major in economics and CS.
Uh-huh.
My exposure to the neural networks is limited to an online course, which I did not complete, hence nil. So starting professional.
Okay. Jossie?
Yep.
Okay.
Yep, I'm Jossie. I'm a junior CS math major here at Mud, and I'm just curious about neural nets and don't have any background. So
Okay. And you're Sam?
Yeah. I'm Sam. I'm a CS math major at Mud, and I've heard neural nets are useful as well.
Will?
Yep. I'm Will. I'm a CS math major at Mud as well, and I have a little bit of background in data science and machine learning, and I'm excited to learn more about neural networks.
Okay. And
I'm Danny. I'm also a CS math major at Mud. I took machine learning and big data here, but we kind of skipped over the neural nets part because there's a course on this, so I'm hoping to fill the whole.
got it. So you did like random forests and support vector machines and
Yeah.
what else?
Regression, softmax.
Got it. Okay. All right, well, thank you. That sounds like most of you are all in pretty much the same situation, which is you don't know a lot about it, but it seems interesting, and that's fine. And you don't know a lot about machine learning, and that's also fine. So we will sort of run from there. The way I'm going to be running the class is definitely a combination of sort of theory and practice so that you guys are jumping in, getting started in using machine learning for carrying out various tasks fairly quickly. We will be using that as a rationale for learning about how it all works, right? So we're going to start as a user of it and then very quickly get into implementation and so on. But the analogy is kind of like, let's say we were trying to teach some, 11-year-olds how to play baseball. Okay, there are two basic ways you could do it if you look at the extremes. One way you can do it is you sit them down and you can go through the rule book, because I guess there is such a thing, and teach them exactly sort of what a strike is and what the strike zone is and what all the bases are and how many people are on a team and what happens with 3 strikes and if you get foul balls and walking, and also teach them about bunting. And then after they have successfully shown that they understand all this by taking some quizzes, then you could take them out onto a baseball field and say, let's play. And surprisingly, or maybe unsurprisingly, they probably wouldn't even know what to do. Okay? The other alternative is you take them out on the field with a ball and you kind of start playing. You don't get into bunting, and maybe you don't even have strikes and balls. It's just like, let's kind of hit it and start going. And a lot of it is going to come by intuition, and a lot of it also will come from interest, right? It's a lot more interesting, in my opinion, to start playing baseball, even though I'm not a particular fan of baseball, than it is to learn about baseball thinking that one day you'll actually get to do it. That's the idea here. We're going to start doing stuff early, and that will help motivate kind of all the rest of it. Okay? And also you get to see where we end up. Does that make sense? All right. So let's get started. Our first problem is a classification problem. So we're given a bunch of pictures of cats and dogs, and we want to distinguish a cat from a dog. How hard is it for you guys to do that? Not hard, I hope. So, okay, so yeah, I would say we have 3 dogs and 3 cats. That's my guess here. And this comes from a competition on Kaggle. How many of you have heard of Kaggle? Okay, so most of you, Kaggle is I think they got bought by Google in the last year or two. And it's basically online machine learning competitions. A lot of them for money, right? So a company will come in and say, gee, I want to have better forecasting, let's say, for my grocery store sales across the country or something. And they'll come in with all that data and then give out a prize of $50,000, let's say, to the person who does the best, the person or team who does the best at that. So cats and dogs is a sort of a simple starter competition. It's interesting kind of to look at it. Came out, I think, in 2014, I believe, 2013 maybe, and to see kind of what state of the art was then versus what you can do now. So state of the art then, when the competition started, was about 80%. That is, that you could teach a machine to recognize about 80% of pictures, which were of either a cat or a dog, and whether it could tell whether it was a cat or a dog. We'll do a lot better than that. So the idea of machine learning, or at least here, what we're going to call supervised machine learning, we have a bunch of labeled data, right? In this case, we have a bunch of pictures of cats and a bunch of pictures of dogs. I think we're going to end up with like 12,000. I think we actually have 12,500 of each rather than 12,000. Okay, so lots and lots of examples of cats, lots and lots of examples of dogs, and they're blurry, and like this picture is blurry, and they're just showing the animal, and there are some that are just showing the face, and so on, just all sorts of different examples. And then, what are we trying to learn? It's a question. What are we trying to learn? Yeah. Given, and this is a key point, a new image. So we don't want to know, having seen this particular dog, can you recognize that this is a dog again, right? Well, that's the problem I have in trying to get, given you, can I figure out your name? Because I was given that label, and can I remember it? So, but that's kind of a memorization problem, right? When I'm trying to memorize all 27 of your names. That's not what we're trying to do here. We're trying to generalize to novel pictures of cats or dogs and to be able to figure out what they are. Now, we're probably not going to do a very good job if the cats and dogs we see are completely different from cats and dogs that are here. Let me try and give an example. Let's say these are all photos of cats and dogs, and instead you get a ballpoint pen sketch of a cat or a dog. Might not be easy to do. Okay. So we want to predict a category for other, that is novel, images. We want to be generalizing our knowledge here. And the way we're going to do that is we're going to come up with basically a probability. Since it's a binary classification, it's either cat or a dog, we can just look at the probability that it's a dog. And we know 1 minus that is the probability that it's a cat. Okay. And we're going to use probabilities for a couple of reasons. So the machine we're training is not going to just learn to output, let's say, a 1 for a dog or a 0 for a cat, but instead this probability, so that we can get some idea of how sure it is, and also we can use that to try and train it better. So that if we find that it only thinks this dog is 60% sure it's a dog, that we know there's some room that it needs to sort of to work there to learn. Okay? So probability of a dog given this image is, what would you say? I think 0 is too low for this. I can imagine a freaky looking dog that this could be a dog, right? And so I'd say maybe a, I don't know, 0.1, 0.01, right? But I would definitely not say a 0. Probably this is a dog. I'm going to do 1 or 5 9s or 8 9s. It's, to me, pretty much a dog, right? So you don't agree, all right. But that's what we're trying to learn to do. We're going to be using, in this class, Python, in particular Python 3. So you guys all have some familiarity with Python? Does anyone not? Great. Okay. Jupyter Lab. How many people have heard of that? Or Jupyter Notebook? Okay, so more than half. So that's basically an interactive environment for documenting and executing Python, let's say. NumPy, which is a library for doing numerical work. So things like array, matrix multiplication and stuff like that, written in C, so it's very fast, faster than if it were done native in Python. PyTorch, which is a Python framework for doing deep learning. Although my original description of the class had said that we were going to use TensorFlow, we're not. I decided PyTorch seems better for what we're doing here. So, FastAI library is a library that's built, in fact, on top of PyTorch, so we can have, at least to begin with, some very simple APIs to doing learning. We have to, in order to get stuff finished in any reasonable amount of time, use a GPU, right, rather than a CPU. And so, likely, your machines are not going to be good for doing the work we're doing here. Okay? So, what I'm planning on doing or suggesting is to use Google Colaboratory. So Colaboratory is basically Jupyter notebooks that can be GPU enabled. Okay? So you can run them for up to 12 hours at a time, and then they stop. So it's good for reasonably sized problems, the kind of problems we're going to be doing here. If you have a nice gaming machine at home with a GPU, then fine, use that. I use my home one as well. And Clouderizer is, I think it's a one-shop company, one-person company. We'll look at that more later. Basically, they provide a nice way to package up running a collection of sort of a distribution and also a good way of sharing your data using Google Drive so that the stuff gets saved and restored. So that will help alleviate some of the problems with Colaboratory, where you can just all of a sudden lose your session, either because you hit your 12 hours or because you got preempted, and kind of get back to going again. And then finally, we'll be using Kaggle data. So let's look at kind of an overview of what a neural network is. Let's not. Let's first oh, this always gets me confused. Let's see. All right, where would my Chrome window go? This is not really what I want. Let's see. That's what I want. All right, so I started this running in Colaboratory before we began class, and it's unfortunately still running. Let me check something else. So this is my machine at home, which has a GPU, and which is not on the network. So I'm wondering whether it lost power or something. So here's what we're going to do. We're going to let this keep running. I wonder how long it's been stuck right there. I'm going to run a second one with a different account as a backup. So you're getting to see some of the stuff that I didn't really want to have to show you yet. So we're going into Collaboratory. We're going to go through this all in detail. This should have been all prepared before we got here. We're going to change to use a GPU. I'm going to run my special Clouderizer stuff to get stuff all started. And it's now starting up. So let's go back to what is a neural network, okay, just to get some brief understanding of it. And let's say in our particular neural network, we're looking at images like, I don't know, cats. Ugly cats, right? So this gets fed in to a neural network. In what way does it get fed in? Like, what gets fed in? Say it again. A matrix of pixels, exactly. So we'll have, I don't know how big this is, 200, let's say, by 200, by a depth of 3 if we're doing RGB. And so those are basically going to be 12 times 10 to the 4th different inputs. Each input being what? A what? A color. So would it be, how do we represent that color? Say it. 0 to 255. Yeah, so we're going to have 12 times 10 to the 4th. 0 to 255 integers. Okay. So I'm going to represent that with a bunch of circles here. Okay, and those are our input. And those are then going to get fed into a bunch of neurons. Now, the exact architecture of this, we're going to get into a lot more detail. For now, I'm going to just kind of show as if every one of these hooks up to every one of these at the next level. Okay? It turns out that's a lot of connections that we don't actually necessarily want. But what's going to happen here, let's say at this particular one, is it's going to get given all these inputs of all of the pixel values and going to do a weighted sum of them. And then apply a little function to it. But what we'll spit out will be, out will come a number. So out comes one number, and in we have a bunch of numbers. Right? And then we'll do it again. Right? So we'll have another set of units, and they'll all be connected. And it will have a bunch of inputs. It'll have weights that it has learned for every one of those edges, and then it's going to output a number. And we keep going, sometimes fairly deep, which is where we get the deep learning part. Right? So yellow is probably not a good color. What's the final output going to be? a single number. So that means our last level here is going to be a single number. And it's going to output a number between 0 and 1. So we'll force it, in fact. Remember I said we're going to do this weighting and then apply a function. The function we're going to apply here is going to force and make sure that we end up between 0 and 1. Okay? Because we know the neural net should be predicting numbers 0, 1, and if we force it to be between 0 and 1, it's a lot easier for it to learn than for it to be trying all sorts of numbers, right? Negative 5,000, you say, no, 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 I really want it between 0 and 1, and 5,500, no, 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 I want it between 0 and 1. We just force whatever it happens between 0 and 1, and then it'll learn from there. So the output is in the range 0 to 1. Okay? Let me just see how it's doing. Let's see. This is not being very friendly. Now it's being friendly. Okay. And let me check and see what this one is doing. That's stuck at the same place it was before. And this one is doing stuff, so I guess that's okay. So let's go back to our picture here. So we have these various layers, right, of our neural network. And the input layer is our pixels. The next layer, right, and we're going to, in a way we haven't described yet, teach the neural network what the appropriate weights are such that the right things happen, such that you get good outputs that happen. But it's all going to be basically a matter of adjusting those weights. The beginning layer, it turns out, is going to start learning particular information or features about the input. So we can look, for instance, at this first layer and see that this unit here seems to be learning diagonals from, with a slope, a positive slope. Kind of. And here are some examples of images that cause this particular neuron to activate a lot, right? So this neuron this unit gets very excited by these sorts of images. Whereas, let's say this one gets excited by these images. So the correspondence between these 9 and these 9 is that these are all examples of things that cause this particular unit to fire. And this is giving us kind of a pictorial representation of roughly what it likes. So the first layer is going to learn some low-level features. And then the next layer, like layer 2, is going to learn some larger ones. For example, here, let's try a different color. Here corresponds to these guys. So it's circular-ish type objects. I'm not even quite sure how to describe them. And here we're getting kind of vertical, or mostly vertical, lines. Now, as we get deeper into our network, it's going to learn even more higher level features. So here, this one seems to be wheels, or even wheels on cars, maybe. And this is kind of a honeycomb or square pattern. And these seem to be pictures of people. And then as we go to an even higher level, we've got things like, well, we found some dogs here. These are birds that stand on who knows what these exactly are, birds that stand on legs, as opposed to, I mean, there are birds that swim, right, or birds that are flying, and it's not those. And then here we got a bunch more dogs on the right, flowers of various types, and so on. One common thing to do in machine learning and deep learning is what's called transfer learning. That is where you learn one task and then use that knowledge to help solve a different task. And that's actually what we're going to be doing in our cats and dogs examples. Rather than creating a neural network from scratch that's completely uninitialized, where we have to train it to get the right weights, to get to learn all this stuff, we're going to actually take a pre-trained network. And that pre-trained network is on, let's see, a bunch of ImageNet images. So it was trained with its, I don't remember how much, certainly more than 1 million images. And it learned 1,000 categories. Okay, so this was this large number of images which were labeled. Okay, and some of those categories happen to be particular kinds of cats and dogs, and there's all sorts of other things, bicycles and cars and trucks and stuff you see in photos. Okay? And so what happens is we got our neural network, right? We got a bunch of inputs, we got a bunch of layers, layer 1, layer 2, layer 3. In this case, there are a lot of layers on the particular architecture of our neural net we're using. And then at the end, there are a bunch of output values. How many of them? 1,000. Each one outputting a number between 0 and 1. And the sum of them all is 1. So they correctly, and again, we're going to force it to do that, so that it's correctly producing probabilities. So the probability of this one may be that it's a cat, or maybe it's a Himalayan Maltese cat, or whatever that particular label for that was. The probability of this one will be that it's a truck. The probability of this one that it's a woman on a bicycle, or whatever our 1,000 categories were. Okay. Training this network takes a lot of time, a lot of this data. And so the idea is, now that we've trained it, let's save it. Let's save all the weights that we learned. And now we can reuse anytime we need. We can have an image classifier that classifies into these 1,000 images. And what we're going to do is we're going to drop this very last layer. And we're going to keep every layer before it. Okay? And we're going to replace this last layer with a single unit that's going to tell us whether it's cat or dog. And so from the last layer, there are going to be a bunch of inputs into here, right? That used to go into all 1,000 and now just go into this one. And these weights, do we know what they should be? We have no idea. But all these previous weights are probably pretty good. All these previous weights know how to recognize lots of different things, or at least provide high-level features for recognizing lots of different things. And so there's probably good stuff in there for whiskers and eyes and fur and stuff like that. And so therefore, all will train as this last layer. And that should go relatively quickly. And not require a lot of data. The larger your network is, the more things you can set about it, like the more weights there are, the more data you've got to provide in order to do a good job. And we're going to be going over all this again, right? This is really just an introduction to it, and partially it's waiting until the sample the machine starts there. So let's see. Let's see if it finished. Yeah, so we've got two dead machines here. So let me just figure out the best way to do this. All right. Sorry. Let me go to my GitHub account and this will be much less interesting because it's not live. This is completely canned. So we'll pretend we're executing this, and we'll see what happens. All right? This is much less interesting than the planned demo. So we have these dogs versus cats competition. As I said, at the time in 2013 that this was done, the cats versus dogs, sort of the best was like 80%. So not particularly good. So this is a Jupyter notebook. When we run this Jupyter notebook, we're going to be running it on a machine that's GPU enabled so that stuff finishes in a reasonable amount of time. You know, I suppose if you want to run stuff on your local machine, you can, at least to make sure it's syntactically correct and so on. But the learning will just take forever if you don't use a GPU. So what happens is each of these are different cells. So there are text cells and there are code cells. These are code cells, these are text cells. The text cells are edited in Markdown. How many people are familiar with Markdown? I mean, it's a simple text editing format. So we have a combination of text cells describing what's going on and code cells that we actually execute. So you can imagine we execute these imports from FastAI, and then we have the dogs, cats data. So we just set a path for that. The size we're going to use, we're going to resize all of the images to 224 by 224. Okay? They come in various sizes, and so we really want to have some uniform size. We can check and see basically, do we have a GPU set up? In particular, an NVIDIA GPU, which is what we need. I'm going to skip that one a second. So if we look at the path directory, what's in there is a temp directory that's used to just temporarily store stuff, a validation directory, and a training directory. And let's just look what's in the validation directory. Dogs and cats directories. And within, let's say, cats is a bunch of cat pictures. So we basically got a directory hierarchy, and at the bottom of that directory hierarchy are a bunch of cat pictures in a cats folder and a bunch of dogs pictures in a dog folder. And if we look at a particular cat, image, this is what a particular image looks like. We'll be talking about the difference between training and data sets and validation data sets. But the basic idea is training data set is what you actually train your model on. So how you learn all your weights. And the validation set is something you run after and say, well, how good is this model actually? How well does it generalize? Okay. So let's look at this cat image. If we look at its shape, it's 445 by 462 by 3. What's the 445, 462? Yeah, the dimensions, the 3, the depth, the R and the G and the B values. If we look, for instance, at the first 4 rows and columns of this, basically, or really the intersection, the top left corner, we get these RGB values. So R and G and B and R and G and B and so on. Now that I think about it, or surprisingly, no, that makes sense. If we look at the very top left corner, it's a gray, right? And so it's a uniform gray for all these 16 pixels. All right, so we're going to use a pre-trained model. The name of the model is ResNet 34. 34 has to do with the depth, so it's 34 layers deep. There are larger and smaller models. And we're going to use some of these fast AI libraries. So the first one is an image classifier data. So that defines the data for the image and says we're getting it from paths, that is from directories, as opposed to some other format like CSV file or something like that. So we put in the path we described. These are transformations. We're going to just ignore that right now. And then we say, OK, let's create a convolutional learner, because this is actually a convolutional neural network. For ResNet 34, the data we just had in here, pre-compute equals true. I'm going to skip that for a moment. And then fit a model to this. So we're going to learn. And what happens is it chugs away and does one. So 2 here says the number of epochs. An epoch is epoch. So this is one run through all the training data. So we're going to do how many runs? 2 runs. So it's going to see every cat picture and every dog picture twice. There were 12,500 total pictures. We actually broke apart. I don't remember how many. I think it's 1,000 of each for the validation, and the remaining 11,500 each for training. So it's going to be going through about, approximately 50,000 pictures. Okay. And GPU is really handy here. We're doing a lot of matrix multiplies and other stuff that GPUs are ideally suited for. So for each epoch, we see a thermometer bar basically as it runs. And then when it's done, it just prints out what's the training loss. That is, we have this loss function that says, how good are you, model, at your output? That is, let me back up a second. So the training loss is really the thing we are trying to optimize. Okay. So this is kind of how far away are you from getting the right answer. And we expect that to go down as you do more and more training. What does val loss mean as opposed to train loss? Francois. So I'm going to just make one small change there. Instead of saying how accurate are we, let's just say how good we are. Not on the training data that you actually built the model on, but on this validation data that we saved aside. Okay? So this is giving us an idea of how well are we generalizing to novel images. And so we'd like this to be going down as well, although it actually went up a little bit right here. Okay? And then the accuracy is just kind of strictly from a 0-1 point of view. Are we accurately saying it's a cat or a dog? Right? Even if you only thought it was 60% a dog, we're going to still give you full marks for that. Right. So in order for this to run, it takes between 20 seconds and 3 minutes, let's say, on my machine. So between 20 seconds and 3 minutes, we can get 98% accuracy, okay, which was as good as the winning examples 5 years ago. Remember, going into the competition, it was about 80% was the best example. Coming out was like 98. Yeah, 98.9. And so we can beat that in, again, between this 20 minutes and 20 seconds and 2 minutes. And the reason that basically subsequent times you run are faster, one reason is, all those weights, right? We got this big network and all those weights. Well, we actually download them from the net first time. So there's that cost of maybe 45 seconds to download the weights. And from then on out, it's quicker. And I'll show you in a little bit the second optimization that happens that is faster subsequent times. So let's look at some pictures. So our output here, back up a second, our data, right, if we look at our training data, we have It's normally called x's and y's. X's are normally the input, and y is the output. So you're given x, and you're trying to learn y. Here, we know what y is. These are labeled values. So we've got an array with a bunch of zeros and a bunch of ones. So presumably, the cats are at the beginning of this array, and the dogs are at the end of this array for our training data. And the classes, in fact, that we have are cats and dogs. So we just put in directories, right? Actually, I just assumed that cats was 0 and dogs were 1 because I knew. But we can see from here, by looking at the classes, the data loader up there chose to make cats 0 and dogs 1. Maybe it was using alphabetical for the folder names. It may be random, who knows. But so that's how we can know these are zeros and these are ones. And we can then make a prediction for our validation set that we held out. And for numerical reasons, we don't actually get back the probabilities. We get back the log of the probabilities. So we see here we have a 2,000 by 2 array for these predictions. So what's a 2,000? Basically what happened is we had, right, we had 12,500 cats and 12,500 dogs, right? And we took 11,500 of them and put these over in what training set, or in the training set? And the remaining 1,000 we put where? In the validation set. So we've got a mix of 1,000 cats and 1,000 dogs. And these 1,000 cats and 1,000 dogs are what we've got predictions for. Okay. It's odd that we have a 2 here and not a 1. The 2 is there because it actually is going to provide you both the probability of a cat and the probability of a dog. And guess what? 1 is 1 minus the other. So even though the network actually only has 1, sometimes you're going to have more than 2 classes. So you'll have 5 classes, right? And you'll want this to be a 2,000 by 5 matrix so that you can know the probability of each of the 5 classes. So if we look at our log probabilities, the first 10 of them, we see here it's probably easier if we took the exponent of these, right, and see that we got numbers between 0 and 1. So let's just look at this one. We have a number here which is very close to 0. So e to the 0 is 1. So it thinks this is a cat, and e to the negative 9 is a number pretty close to 0. So it's pretty sure it's not a dog. Okay? So presumably, at least the first 10 of these are actually cats, assuming this is doing a good job at classifying. And what we can do is we can go ahead and, for instance, look at some correct labels. Like randomly, here's a dog that it's predicting with high certainty is a dog. Here's a cat it thinks is a cat. Another cat it thinks is a cat. A dog it thinks is a dog. And we can look at some incorrect labels as well. So here, it's 70% sure it's a dog. It's actually 2 humans and a doggish-looking cat. Here, well, this is I guess a cat's teeth would be sharper. So that's a dog's mouth. Here, yeah, a logo about pets. What happened there? Your data is not always clean, right? You have things that are incorrectly labeled sometimes, just kind of garbage things. You might have things that are very blurry. Who knows what you're going to get? So that sometimes happens. So I don't feel bad about it failing on this one. And this, it's fairly sure, it's 90% sure it's a dog, but it looks like a cat to me. And you can also get a look at the most correct cats, the ones that were closest to 0. So you can see here, I guess, yeah, those are cats. And these are the things that it was really sure are dogs. And then the most incorrect cats are interesting too, right? This logo. This is 98% sure it thinks it's a dog, which it could be like a Chihuahua or something. Here, I have no argument that it failed that, right? Oh, this is a picture of a cat, not a dog. It sure looks like both to me. And I don't know how it got this one. And then some most incorrect dogs. Again here, this one is just not surprisingly, it's a logo. This has some cat features to it. Yeah. And then the most uncertain ones, the ones that are closest to 50%. Yeah, our teeth, this thing, another logo. Yeah, so. All right, 1 second. Yeah, that's just not going to be coming back. All right. So that was our brief introduction, where it would have been really neat to watch it really quickly move a thermometer across, and then we would have seen everything the same. But you would have seen the thermometer moving, and you would have felt this sense of progress and completion. So we'll tackle that again on Monday. And now getting to just formalities. So syllabus. You could just pass that out. So everything online is going to be on Piazza, or Piazza. So please sign up for that. I haven't added you already. I think you can add yourself, and that's probably the best way to go on that. So do that kind of immediately. Let's run through that. So office hours. So I'll go through the syllabus itself in just a second, but I wanted to go through the Piazza kind of to give you an idea here. So my office hours are not on the syllabus. So I'm going to be here for 30 minutes after class, and then I'll be in my office in Olin 1255. You mean more? I don't know how we have extras, but okay. Mondays from 1 to 2 and Wednesdays from 1 to 3. If those times don't work for you, contact me and we can set up an appointment for some other time, probably on a Monday, Wednesday, because that's when I'm normally here. Resources. Resources is not yet public. I did not realize that. So I will have to make that public. So the resources will look like this once it's out. So we have the syllabus, a schedule and cheat sheets. Let's start with the syllabus. My email is here. My preference would be, rather than using email, use Piazza, and preferably use public messages rather than private ones. For two reasons. One, other students can answer if I'm not available. And second, it's likely it's a question that's of interest to other people. So if you have a personal question, then certainly send me a private message. And if you need to send email, you can send email. The course description, I think it's very interesting to look at this, what is at least 9 years old description. So modeling, simulation, and analysis of artificial neural networks and their relation to biological networks. Design and optimization of discrete and continuous neural networks. Backpropagation of the gradient descent methods. Hopfield and Boltzmann networks. Unsupervised learning. Self-organizing feature maps. Applications chosen from function approximation, signal processing, control, computer graphics, pattern recognition, and time series analysis. Relationship to fuzzy logic, genetic algorithms, and artificial life. So, in 2009, and I don't know how much older this course description was, but in 2009, neural networks were much more of a backwater than they are today, right? It's really in the last 5 or 6 years that they've suddenly taken off. Does anyone know why? Yeah. So high accuracy with the ImageNet data set. Yeah. And part of that had to do with how did they get high accuracy? Okay, so design of the architecture, convolutional neural networks. Yeah.
They have more processing power.
More processing power. Like, for instance? GPUs. Yeah. No one had thrown GPUs at the problem until 5 or 6 years ago. Okay. And there's a lot more data. So if you think of the ImageNet, which is, as I said, more than 1 million, I think it's probably more than 10 million. 10 million labeled images, that's a lot of labeling you have to do. It's a lot of data to actually just get humans to do that labeling. And so, as well, the more data you have and the more labeled data you have, the better your models can be. So the better trained you can go. So there's kind of this cycle of coming up with better models and then coming up with more labeled data. Give me an example of where you, let me finish the syllabus and then I'll come back to this. Okay. So what we're going to be doing is much more deep learning, where it's these deep networks. And that's part of what's happened in the past 9 years. We've learned how to successfully train a neural network that is 10 or 50 or 100 layers deep. And before, we didn't know how to do that. We'll learn why later on, what the problems are with that, and kind of how that's been worked out. In text-to-speech, speech recognition, image labeling, captioning, we're going to be looking at the theory and practice, as I said, so the practice as well. Backpropagation, convolutional neural networks, which are how we do image processing. Recurrent neural networks, which are how we'll do things like translation. Long short-term memory, which is a kind of a way for a neural network to remember things long-term. Reinforcement learning, because I have particular interest in that in games. So we'll look at the AlphaGo stuff that was done with DeepMind for Go and chess, some of the stuff with Atari. Every lecture, I'm capturing the screen contents and the audio, and I'll put that up with a link, so it'll be on YouTube with a link. Please don't use this as an excuse not to take notes, but I think it can be useful to refer to later, and so that's why I provide it. But I can't guarantee it'll always work. I'm sure there will be some glitch at least once where the lecture doesn't get captured. The grading, so programming assignments will be 30%. Our first programming assignment will probably be, if not next week, no later than the week after. And we'll have, I'm going to skip scribe for a second, 2 exams, a midterm and a final, worth 25 and 40%. And then 5% of your grade will be acting as a scribe. So the idea is to capture lecture notes, put them in a written form in a Google Doc, provide links to the video as necessary, to particular time spots within there. And since we're doing it on Google Docs, the scribe is going to create an initial version, and then if you find that the notes are wrong in any way or need more, you'll go in and edit those. So kind of like a wiki. So we will have sometime, I'm going to go ahead and act as a scribe for the first 2 lectures to give you guys an example. So today's and next Monday's. And then starting on Wednesday, we're going to have someone else be a scribe. So come Monday, I'll have a sign up for you to do that. Make sure to sign up on a day when you are not otherwise swamped, because the goal is really to get that kind of turned around within 24 hours. So it can be most useful to other people. Questions on that?
Is there a particular day in the week when assignments will usually be due, or?
No, and I'm open to suggestions. Yeah. Grades. We're not grading on a curve, so it's 90%, 80%, 70%, 60%. And pluses and minuses kind of as appropriate, like minuses and then nothing and then pluses. That's, I think, a good ordering. And it's possible I can lower those standards, but I won't ever raise them, right? So if you get 90%, you're guaranteed to get some sort of an A. It's possible you may reduce A minuses to 89 or 88 or something else, but I reserve that right. Honor code, you're all bound by the HMC honor code. I think whether you're in HMC or not, there will be some group assignments. And so if you're working on a group assignment, the idea is all the work is that of only that group and not other groups. And it's really important to know that every person in the group is responsible for that entire assignment. So it's not okay for one person to do assignment 3, and that's in the same group, someone else then do assignment 4. One way to think of it is you're all jointly and severally liable for the work. So if someone hasn't worked on a particular assignment, note that as part of the submittal. And I'm probably going to just do pairs working on this. If you need accommodations, there's where you go there. The gender-based misconduct policy, I have to report if you say something to me. I think that's about it. Questions about anything? If you go back to Piazza, we have a schedule, and the schedule contains kind of what's happening what day, at least to the extent I know so far. What would be helpful reading? So we have no assigned book, but there is a deep learning book, which is available online. I suppose you can buy a copy if you want, but it's available for free online. And I will be pointing out some useful readings there. And I may also have references to articles and other sorts of things. Okay? But when I say helpful reading, I'm not going to quiz you on it or anything, but it would be helpful if you read it. And I will have a link then here to the video on YouTube. So sometime I would expect this afternoon I'll have that available. And that's really interesting because this all shows next Monday. So, oh, yeah, that's correct. All right. Helpful reading for next Monday is this. This is what we're going to talk about next Monday. And this is what we talked about today. And I'll film the video here. Questions? All right. Let me just, since I have 5 more minutes, get back at something I didn't get a chance to talk about. And that was a speed up that is done with this pre-trained network. So we've got an image that's coming in at the left-hand side of this network, right? Image coming in here. We go through these calculations to figure out the values coming out of layer 1, values coming out of layer 2, all the way values coming out to the next to last layer. And then we've got this new layer with these weights here. And remember also that we run often multiple epochs. In the example I show here, it was 2 times through every image. But sometimes you may run 10 or 20 or hundreds of epochs. Okay? As long as things are continuing to get better, it's a good thing to do. When we have an image coming in here, in the first epoch, if we have a single image, and we look at the outputs of this next to last layer, is that going to be any different from the 10th epoch for that same image coming out of this last layer? No, because we pre-trained this, and when we're just trying to learn these weights at the very end, okay, to our final single unit. So therefore, what we can do is pre-compute what are called the activations of this next to last layer. So one time, go through, take an image, feed it through layer 1 to layer 2 to layer 3, all the way to layer n-1, and then take the output of what's coming out of layer n-1 and save it to disk. And say, for this image, here are the pre-computed activations. And that means it'll be much quicker, right? Because all we have to do is take the image, find its associated activations, go to this last layer, and say, okay, let's go ahead and do some learning on these last weights. So that'll make every epoch much quicker. However, we'll have to pay one time to pre-compute these activations. So that's the other cost that's associated with doing our learning. That's a one-time cost. Now, we're going to be looking at making our classifier of dogs and cats even more accurate later. Like, we learn good values for these weights. Let's go back and do some more learning again, running more epochs, and let's tweak these weights of the previous layers. Okay? So, because if we make slight modifications, maybe we can get even better. Right? We're using the units that were optimized for the ImageNet images, all 1,000 different classes. Since we're just using dogs and cats, we've done good with these weights, but maybe we can even fine-tune these and get a little bit more accuracy out of it. Okay? That's one type of sort of optimization we can do. Another type of optimization that we'll talk about sometime next week has to do with data augmentation. So imagine, if you have a picture of a dog. This is really going to be ugly. Let's see, dog. Okay, well, maybe it's a sheep. So this is a left-facing dog with a huge tail. All right? That dog could have just as easily been facing the other way. Right? So we can artificially create data by taking this image here and flipping it horizontally and saying, hey, now we got yet another dog. In fact, if we take our 12,500 dogs, now we have 25,000 images of dogs. Okay? And this dog could have been on a slight incline, right? So if we take this picture and actually just rotate it 3 degrees, there's another dog. Okay? And it might have been that this picture were cropped slightly. You know, maybe they were trying to hide that really long, ugly tail. Okay? And so that's also another picture of a dog. So we can do some random rotating, zooming in and zooming out, flipping horizontally, and cropping to artificially generate lots more data. Okay. But if we do that, we can't use this pre-computation anymore. Because all of a sudden, as we're going through this epoch, every time we get an actual image, we're going to artificially modify it. And so we've never been through this before. We don't know what the activations are. So it's going to be slower, but we can get a better result. Because in general, as more data, the better. Okay? The more labeled training data. And this provides us a way of artificially generating some more training data from our initial data. That's it for the day today. I'll see you on Monday. Have a good weekend.